One of the questions is asking to prove accessibility of specific functions. And one of them is a conjunction and variables. A conjunction is just a or statement, right? Not conjunction, disjunction. I've never heard it called that before. I was just double checking.
Yeah, so remember, I mentioned that you need to check carefully on the definition of applicability.
Yeah, like it needs to
one particular algorithm across all the functions. Not
But I mean, isn't an or statement just one type of function?
So destruction, of course.
So as long as you prove with that one page that this one, just need to prove that there's given some epsilon. Yeah. So basically, if you just guess yes or true on a disjunction, you're going to be right 1 over. You're going to have error at most 1 over n.
Here you need to be sure that epsilon and delta can be absolutely small.
Yeah.
So one down to the random.
Well, it's not though, right? Because 1 over n is the highest error you'll ever achieve because if there's n variables, then you just guess yes, right? Okay.
Okay, good afternoon everyone. So let's start. So first reminder again. So tonight is the deadline for the homework one. So we have already extended the deadline to Wednesday, right? So don't forget to submit your homeworks. And because I just checked the counters, there are only 18 submissions. I assume that you have all of everybody has finished homework, but just want to submit by the last minute. That's okay. Be sure not to pass the line, otherwise you'll incur a penalty. And I will suggest you to the homework 2 as early as possible. considering some of you might now fully adapt to this kind of schedule. So I extend 3 days, but for homework 2, we shouldn't have actual extensions for that. And you will see that because you have implemented your decision trees, and homework 2 only require you to do some simple modifications on your decision tree implementations to implement like boosting and backing algorithm. Pretty straightforward. Okay, so all you need is just spend some time testing data and run and record the results. It still takes some time, but won't make you struggling. But again, do it early. Okay, so let us continue the linear model introduction. So linear models, as the name suggested, so it is determined by suppose we have n features or n variables, right? And the linear model is determined by an n-dimensional weight vector. So one weight per feature and one actual bias parameter. So if you want to use linear model to classify your examples into, say, positive or negative examples, you just compute the linear function, which is the inner product between the weight vector and the input vector plus a bias parameter. Right? And how can we determine our prediction? I mean, how can we determine this specific example is positive or negative? An idea? Okay.
Which example is this? Is it the one up there, or?
No, not this example. Just the general definition for linear classifier. So giving you an example, you can compute a corresponding function, which is the inner product between the weight vector and the input vector plus a bias term, right? And then how can we determine the label of this example according to this function value?
Whether the output is positive or negative?
Yeah. So our classification, what is our classification function? Or what is our prediction function?
Y is greater than 0 or y is less than 0.
Yeah, we can use just one function to represent what you have suggested as a sign. You just look at the sign of your linear classification function. If the sign is 1, then you predict 1, otherwise you predict negative. Right? So, and then we then introduced some nice geometry view of the linear classifier. And we can, maybe I should show you guys the graphical representation. It's not good to just speak, right? So this is a geometry view of linear classifier. So this line represents the classification boundary. This line can be represented by an equality, right? The equality is the classification function being exactly 0, right? So then on one side of this classification boundary, the classification function itself, that is this function, is always positive. It means that we predict all the points on this side is as positive examples. And all the examples on the other side has the classification function being negative, meaning that we predict them as negative. So this is a geometry view of linear classifier. It's very important. That's why I repeat it again. Right? And also, you need to be aware that the weight vector, the directional weight vector, is orthogonal to the classification boundary. And you can check for that. It's pretty straightforward to check. Just compute the inner product between the weight vector and the arbitrary vector, which is which lies on this classification boundary. The inner product must be 0. And then we introduce the location trick, right? We can augment the input vector by a constant feature 1, and correspondingly we can fold the bias parameter into the weight vector, and then our classification function can simply written as inner product between the augmented the new weight vector and the augmented feature vector. And we then discuss the expressiveness of linear classifiers and with some Bloom functions, right? And although the hypothesis space of linear classifiers is infinite, the reason is that a specific linear classifier is determined by a pair of weight vector and bias parameter, which are both continuous, right? So you have an infinite number of continuous vectors and values, so the hypothesis space of linear classifier is obviously infinite. But that does not represent the linear classifier can represent all kinds of functions, right? So for example, of course, these are positive examples. And for example, when a Bloom function has a property called parity, then we can show that the positive examples, negative examples are not linearly separable. You can never find out the line to perfectly separate positive examples from negative examples. A typical example of such kind of parity function is called XOR function. That's a famous example, famous counter example proposed by Maraminsky, and to illustrate the limitation of linear classifiers. But we mentioned that there's a smart trick to overcome this issue. What is the smart trick? Of course, in the original domain, right, in our original input space, linear classifiers are not powerful enough for a few cases, right? For example, in this case, the input dimension is just 1, x, only one input feature. So those are positive, those are negative. You will never be able to find out one line to separate all positive from negative examples, right? But how can we deal with this case? We still want to use linear classifier, but to separate those positive examples. How can we do that? We introduce a trick. It's called a feature transformation or feature augmentation, right? So now that in the one-dimensional space we cannot find a linear classification boundary, why not we augment the feature, each example by one extra feature, which takes the square of the first feature. And now each instance is represented by two features, right? X and x squared. And now if we draw the locations of those examples in the two-dimensional space, we'll find that these are their distributions, right? In this new space, new two-dimensional space, they are linearly separable. Right? It's very easy for us to find out a classification boundary which well separated.
I'm just curious, when we add a new feature, like define our own feature like that next to data, is that cause for overfitting at all, like for our training data?
No, that depends. That depends. So you can think it in another way, like in this two-dimensional space, right? So if you put x and x squared as into your linear classifier model, so although in a abstractive form, it is still a kind of linear form, right? But if you fold x2, x squared, not fold, you explicitly write down the terms regarding x2. So the whole function in terms of x is nonlinear, right? It's nonlinear. That's why. So although in a more general level, it still looks like a linear model, but if you write down every details, you find it becomes a nonlinear model. And it turns out this nonlinear model can perfectly separate positive examples from negative examples. But it does not mean that, okay, because I improve my fitting into the training data, I will get overfit. It just improves the fitting. I do not like fit all possible losses in the training. But if you do it like in a more extreme way, like I extended into very, very high dimensional space to put all kinds of non-linear terms. Yes, that could be, there could be some risk to overfit the training data. But generally, this kind of depends. Depends on how you choose the feature mapping. Any other questions? So I just want you guys to have a sense about this feature augmentation, feature mapping trick, because we'll revisit the same idea again. It is particularly useful when we introduce small vector machines. How does small vector machines perform nonlinear classification? The important trick is called feature augmentation. And when you use feature augmentation and you do some smart transformation of the objective into the dual form, you'll see how it works. Yeah. Okay, so this is the exercise left for you, and XOR function. And I want you to try some tricks to do some feature mapping for the inputs of XOR function, such that in a higher dimensional space, you can linearly separate all the examples which are originally labeled by XOR function. Okay. So sometimes we might not need to, even the data is not linearly separable. We might not need to invent some smart feature mapping. That is in the case the data is almost linearly separable. So we can see that this data is quite linearly separable, right? Although we cannot ensure every positive example is separated from negative examples, but we can tolerate a small number of errors. Then it's fine. Then we can just stay in this original feature space and use this classification boundary. Okay. Then the key question in practice is that how much noise do we allow for? There is no answer for that. It still depends on your application, but it just gives you a choice. Sometimes you think, okay, the training error is too large and exceed your tolerance level, then maybe you need to work out some nonlinear feature mapping to largely reduce the training error. But sometimes you think it's fine because there are only like 2 examples are incorrectly predicted in the training data. That's fine. I just keep the linear classifier in the original feature space. So to summarize, right, linear classifier. So it is an expressive hypothesis class. So expressive is first stated into this size of hypothesis space, because the continuous or the parameters hypothesis space is infinite, and many functions are linear, as we have seen a few examples like conjunctions and disjunctions, etc. Right? And often it is a good guess for hypothesis space. Why? Whenever you're doing some kind of learning task, you can always start with linear classifiers or linear regression models, because this is a good guess, and I can tell almost 80% of tasks, or even 85 to 90% tasks can be well addressed by linear classifiers. So if you find that your linear classifiers are good enough to address that, you can just stop it. You do not need to try more. Only when linear classifiers really, really bad, then you can invent some feature transformation trick or use more models, use more complex models such as like kernel methods, nonlinear, artificial neural nets or deep neural nets, and so on. And another practical reason is that the software packages for linear classifiers are really, really efficient, scalable, and mature. So you can find many highly scalable linear models. Linear models implementation in the web is open source. And even in some cases, like like online advertising, people know that the click-through rate or click probabilities are kind of nonlinear to all kinds of features about users and web pages. The people in industry usually don't choose nonlinear models as well. The reason is that it is expensive. Why should I buy like 1,000 GPUs and each one costs like $8,000 to construct a large server on that? I just run linear models. But if I want to add some nonlinearity, just to construct some nonlinear features, as we just said. So this is why linear models are so popular. Okay. But of course, you should be aware that some functions are nonlinear. In theory, XOR functions are some non-trivial Bloom functions. Yeah. And this is about current tree. So the last point I want to emphasize is about the effect of bias term. So why should we introduce this bias term? So it looks like it's not concise, right? So why not we just leave a inner product between the weight vector and feature vector in our classification function? That's it, right? Why should we add an extra bias term? Any thinking on this?
Can you have symmetric about the origin?
Symmetric about origin. What do you mean by symmetric about origin?
Or not necessarily symmetric, but it's not separable units of origin.
Yeah. Any other supplement? Yes, right as you just mentioned, right? If we throw out this bias term, then our classification function is simply w1x1 plus w2x2 to be 0, right? So then the classification boundary will always cross the origin. Right? You can try, right? This if your classification boundary is simply the inner product between w and x is 0. If you take x to be 0, then w transpose x is 0. That means the classification boundary will always cross the origin. So what's the consequence? What's the consequence if your classification boundary is always crossing 0, the origin? You can take a look at some special examples. So suppose we have a bunch of positive training examples surrounding an origin, right? So obviously, we can find a perfect linear classifier here, like this. We can separate all positive examples from negative examples. But if we throw out the bias term, what will happen? Yeah. It just makes the positives, right? So in summary, in one word, the bias term is just to increase the flexibility of your linear classification model. And without that this extra term, then the locations of the classification boundaries is restricted, right? Must cross the origin. That would result in bad effect when the particular set of training examples are surrounding origin. So hopefully you'll understand why the bias term is needed. So so any questions so far? Everyone is good, right? Okay. So so we have finished the introduction of the linear models, and now from now on we will discuss in detail about a few specific linear model learning algorithms. So as we mentioned before, we'll start with linear regression. This the linear model to predict continuous outputs, and then we'll look at different kinds of linear classification models. So the algorithm we learn the linear regression model is called least mean square method. So we'll start with some concrete example of linear regression application, and then we'll introduce the specific training objective for the least square method. As we mentioned before, right? Whenever we conduct the supervised learning, the learning procedure is kind of searching process, right? So inside the hypothesis space, you want to conduct a searching procedure to find out a hypothesis which best fits the training data. That's in general what a learning algorithm does. Right? So in the least mean square method, to conduct the search, we need to evaluate whether a particular linear regression model fits the data well. Now, how can we do that? We need to construct an objective function. The objective function measures how well or how good your hypothesis, namely the current linear regression model, fits the training data. Then our learning procedure is to find out a set of model parameters which minimize the objective function. And to minimize the objective function, we'll introduce the most commonly used algorithm called gradient descent. And as I will say, nearly all kinds of machine learning algorithms, you can implement them with some type of a gradient descent. This is a general framework. And then later we'll explain what's the limitation of gradient descent, especially in the large-scale context. Let's say the gradient descent, the complexity of gradient descent, the cost of gradient descent is too large, and to enable more efficient and more fast update, we'll introduce stochastic gradient descent. That's the outline. So first, let us look at the concrete application of the linear regression model. So suppose our task is to predict the mileage of car, given the weight and age of the car. So can you predict how many mileages, how many miles your car has running, right? So suppose we have collected like 4 training examples. So x1 represents weights in terms of 100 pounds, and x2 represents ages, right? Those are mileage. So I think the mileage is its unit is just 1,000 miles. And then throughout this set of training data, our objective is to learn a function that can predict the mileage using x1 and x2. So it's a typical regression problem. Well, what is it? What is regression? What's regression? What's the difference between regression and classification?
You're trying to fit it to an equation with coefficients that fit x to y.
Yeah, but for classification, we also done same thing.
You continue this output.
Yeah. Yeah. Just keep in mind, whenever we talk about regression, we're doing prediction on the continuous output. And we're doing classification, we're doing prediction on the discrete output. Right? That's the difference. So now we want to learn a function which predicts this continuous knowledge using x1 and x2. And what kind of model can we choose? We can use linear model. So if we use linear model, we assume our output is a linear function of the input. That is, the mileage is equal to W0, which corresponds to the bias term, plus W1 x1 plus W2 x2. Right? W1 and W2 are the weights for the 2 variables x1 and x2. So this is our linear regression model. And the learning procedure is to use the training data, those data points, right, examples, and to find the best possible value of the W, right? W consists of both the feature weights and bias parameter. And then, given the W, and given the values of x1 and x2 for a new car, we can use the learned W to predict mileage for the new car. That's the setting of the linear regression. So now, let us look at how can we conduct the learning procedure. Yeah, and here for convenience, we represent the parameters of the model collected, W0, W1, W2. So put them into a long vector. W. You should get used to this vector representation. So in general, this is some specific example for linear regression for this particular task. But in general, we will assume our inputs are vectors which belong to the d-dimensional space, meaning that we have d features, right? And our outputs are some real number. And we have collected a set of training data, which are pairs of the input vector and output real value. And we want to approximate the output y by a linear function. So remember, we already talked about the representation of linear models. Do you have any questions? Okay. For notation simplification, right? To simplify the notations, we can fold the box parameter into the whole B vector, right? And also we augment the feature vector by a constant 1. So for convenience, we use the notation simplification. That means we can assume x1 is always 1, meaning that x1 is always the augmented feature. And then the following are the original features. Then our regression function is simply the inner product between w and x. This is just a notation, custom of notation. And then to give an example in one-dimensional space, right? So suppose our input is just one dimension, and because we use notation simplification trick, so x1 is always 1, right? So x2 and y, are the output values. So if we use linear regression, and we predict y with w1 plus w2 x2. And similarly, for two-dimensional input, and x2 and x3 are here, and the y-axis here. And the output function is simply w1 plus w2 x2 plus w3 x3. Any questions so far? Okay, good. Looks like everybody is comfortable with this. It's not like previous lectures, numerous questions. It's really straightforward. And then the question in conducting the linear regression learning is that how do we know which weak vector is best, is the best one for a training set? So remember, our learning procedure is to search for the best weight, which corresponds to the model that best fits the training data. Then to conduct the search procedure, we need to know at any time the current weight vector, how does it fit to the training data? Now how can we evaluate this? We need to come up with an evaluation metric. How can we do this?
Measure the error.
Yeah, how do you define error?
Where you're at that line that you plot now, or
Yeah, of course, you're giving very intuitive answer, but can you define some specific formula for that?
use the standard deviation. You do the square root or the square of the
Standard deviation.
It's not a standard deviation, but
Okay. You have a same thing. Okay. So I get a point. I guess you are saying, okay, why not we just calculate the difference between your prediction and the true output, right? And just calculate the sum of the squares and take average. That's not square standard deviation. It's just it's called square error. That's exactly what this mean square method chooses to do. Right? So for an arbitrary input x and y, in training set, we first define the error when our current model predict xi. It's simply actual value of the difference between the ground truth yi and our prediction. So this is also called cost. So this is very, if you call it cost, it's also intuitive, right? So the further away your prediction is from the ground truth, the more cost you should pay for it. So this is also referred to as cost. And then, given the cost or the error defined on one single training example, we can accordingly define the cost for the whole training set, which is simply the summation of the squared cost over all the training examples, or squared error. And then we multiply with this summation of squared error by 1 over 2. So someone may ask why we should multiply with this constant, right? So it is completely unnecessary to multiply with the constant. But as you will see, we want to minimize this cost. You need to calculate the gradient, and when you calculate the gradient, there is an extra constant 2, the coefficient 2 here, right? And 2 and 1 over 2 cancel. So that's the reason we usually preserve this 1 over 2, it's just for convenience. Now you can remove it. You can remove definitively. So this is called a cost function over the training set, but it's usually also referred to as loss function. So of course, for this particular model, the loss looks really simple, right? But you will see in many other models, the loss function can be quite complicated. And in general, if you want to develop a learning algorithm, you will always end up being with a specific loss function over the training set, which measures how well your model fits the training data. Then the learning procedure is simply to find out the model parameters which optimize loss function. So you can imagine, right, when this loss function is the smallest, you arrive at a linear regression model which best fits the training data, right? So then the so-called learning procedure is an optimization procedure to this loss function. So then the question is that how can we find out the optimal weight vector W, which minimizes this square loss? It's also called LMS, least mean square error. How can we minimize this error? An idea? Yeah, exactly. Another idea? Yeah. So we'll discuss about how to set it to 0 and solve it directly. In this least mean square error, yes, it is doable. You even do not need to carry out some optimization procedure. But for generality, I want to introduce a more popular gradient descent method. So a gradient descent not only applies to this particular loss function, it applies to all kinds of loss function as long as it's differentiable. But even when the loss is not differentiable, you can compute subgradient to perform subgradient descent. So it's necessary for everybody to know what is gradient descent. So what is gradient descent? In general, it's just to start with some initial point and then adjust the location of the point according to the gradient direction of the objective function. That's called gradient descent. So let us look at the general framework for gradient descent. So suppose we want to minimize the function JW. W are the parameters we want to optimize, right? And we start with some initial guess for W, say W0. You can start with any guess. So usually you just do some random sample. You get W0, and then you perform the iterations until convergence. So in each iteration, you first compute the gradient of the current model parameters, the gradient of the objective function j at current model parameters wt. Then you use this gradient to update wt to get wt plus 1. How can you get wt plus 1? You take a step in the opposite direction of the gradient. This actually uses the properties or important information contained in gradient. So gradient direction indicates the direction where the function increases. Right?
How big is the step you take?
Yeah, that's a very good question. The choice of the step is really important. You cannot be too large, but as long as you choose a appropriate step, you're guaranteed to converge to some at least local minimum of your objective function. And how many of you have taken the optimization class before? Okay, not too many. So here we didn't mention the specific strategies to choose the gradient, but in classical optimization algorithms, there are a variety of methods to choose the step sizes, such as like a front move search or backtracking search or kinds of those methods. And use those methods, you be guaranteed that you can choose the appropriate step and to ensure the convergence of the others. But for our case, you can simply like choose the step size to be enough small. That's it. So to say why the gradient indicates the increasing direction of the function, we can take a look at the example here, right? So this is the curve of the function jw, and we initially we start with w0. Right? We randomly pick up a point in the x-axis as our initial point, and then we compute the gradient of jw at w0. So we know that the gradient is actually the slope of the tangent line at w0, the tangent to the target function, right? So we can say this slope is positive, it's bigger than 0, because this angle between this tangent line and this x-axis is less than 45 degree, right? So the slope must be positive. And now if I want to update w0 toward the opposite direction of the gradient, then where should we move w0? To the left or to the right? Any other idea? Any idea? Yeah. So this one is positive, right? So the opposite direction of the gradient must be negative. You add w0 to some negative value, you actually move w0 toward this direction. So we get w1. And now we can say what's the function value changes when we move to w1. Our function value is decreasing. And similarly, if you like want to, if you move toward the direction of the gradient, you're gonna move on the right hand side, right, from this way, and then you increase the function value. But now we want to we're gonna minimize the function value, so we move toward the opposite direction. So it's along this way, and we decrease the function value. And similarly, we can compute the gradient of the function at w1. You obtain a slope which shows that the gradient is positive as well. Right? Then you should update w1 toward this direction as well. Right? You get w2, and similarly, you compute gradient, update w2 toward the opposite direction of gradient, you get w3, and do it again and again until you converge. So this is the whole procedure of the gradient descent. And let's do the reverse proof about why gradient descent the y gradient is a direction to increase the function value. It's really, really simple. You can just expand your function using Taylor expansion. And you'll see that. Just do the first order Taylor expansion. You'll see that. And you'll see that when the step size is enough small, then the second order term is can be ignored, right? And the whole function is wholly determined by the first order term, which is the gradient part. So now let us put this gradient property step into our least mean square method. So we initialize. So this is our GW. This is our objective function, right? So it's a summation of the square error over all the training examples divided by 2. And then we initialize our model parameters with W0. Then we go through many iterations. In each iteration, we compute the gradient of our objective function at the current all the parameters Wt. Then update Wt by subtracting by minus some step size r, multiplying with the gradient. Then we get Wt plus 1. And then R is called learning rate. And later we'll discuss how we choose learning rate and why learning rate is important. And then the next step is how can we fulfill this gradient computation? How can we compute this gradient? What is the gradient of our objective function? So first we should be aware that the gradient with respect to W is a vector. Because we have multiple input features, right? We also have a bounce parameter, which are folded in the weight vector. So the gradient is essentially a vector, where each element is a partial derivative of our objective with respect to some specific feature weight. Then remember our weight vector is consists of d elements. So our weight vector is a d-dimensional vector, right? So corresponding to the weight vector, the gradient vector is also d-dimensional. Then let us look at how can we compute the gradient vector. We'll start with computing the gradient or the partial derivative with respect to each specific weight. So take the j weight as an example, right? We want to compute the partial derivative with respect to wj. So just substitute this specific objective function for j, right? And then we take the partial derivative for wg, and we just put the partial derivative inside the summation. Right? Then what is the partial derivative for this square sum, for this square error? We just use chain rule, right? This is we can treat it as an integral part. So it's some like a z square, right? And you take gradient. You first take partial derivative over z, which is 2z, right? That is here. And then you take the partial derivative over this error. And because we only take partial derivative with respect to wg, so all the other terms which do not contain wg are treated as constant. The partial derivative are 0. So the partial derivative for this error with respect to wg are simply minus xij. Xij is the g feature for ith example. You have a minus sign here, so you can move it out. You end up with your partial derivative for a specific gradient, for a specific feature weight. So this is just one element of the gradient vector. Obviously, if you want to compute the whole gradient vector, you need to go through all the feature weights and compute their corresponding partial derivatives. And you can say this is actually this gradient. The result of this gradient is actually interesting. You can say this is simply a summation of the production between each error. The error of each training example and the corresponding feature input. If you compute the partial derivative with respect to j feature, right? So just sum up the area. Predicting each examples, multiply with the objective feature in each example. That's the gradient. Of course, you need to put a minor sign outside. That's a interesting observation. Any questions at this computation? Okay, so now we can plug in this computation in our gradient descent for this mean square method, and whenever we are in a like t iteration, we will compute the full gradient vector. We need to go through all the training example and compute the partial derivatives for all the feature weights. And when we collect the partial derivatives for all the weights, we have the gradient vector. Then we update the weight vector by this formula. And we do this until the total error is below the threshold. So you have various ways to measure the total error. One way is like you can compute the total training error. So if your training, so the training error is below some threshold, say 10 to minus 5 or 10 to minus 6, you can exit. Another way is that just compute the difference between the weight vector in current iteration and weight vector in previous iteration. If the difference, you usually take a norm because it's a vector. If the norm difference is smaller than some threshold, you can exit. So these are two commonly used strategy to stop your gradient descent learning algorithm. In your implementation, you can choose whatever method you want. And here, again, R is called learning rate, and it's a small constant. And the gradient descent has a very nice property that whatever objective function you have, as long as it's differentiable, and the gradient descent is guaranteed to converge to a local minimum of that objective function. So what is a local minimum? Local minimum means that, okay, if you say some point like x0 is a local minimum, that means in some set which include in some closed set which include x0, all the function evaluated on all the other points is bigger or equal to the function value at x0. So you can imagine in a local region, at a particular point in the function reaches the minimum. This is called local minimum. A local minimum is different from global minimum. Global minimum is that, okay, across all the input, right, across all possible inputs in the whole domain, what's the minimum function value? It's different. Any questions? Just briefly review the concept for global and local minimum. Everyone is good, right? So, but for our case, for this mean square method, because the objective function is convex, then local minimum is totally equivalent to a global minimum. That means your gradient descent can always return a global minimum of your objective function. So that's a good point. So this mean square objective is the first convex loss function we meet in the machine learning algorithms. So as we proceed, we'll see other convex loss functions. The convex loss function has a particular benefit is that you do not need to worry about your learning algorithm was trapped in some bad local minimum. As long as you find some local minimum, you always find a global minimum. That's a very nice property. So later, when you design your own learning algorithm, you can try to invent some convex loss function rather than non-convex ones. Okay, so this is a general idea of gradient descent, but it also has nice property, right? Convergence guaranteed to the local minimum, and if your function, your objective function is convex and global minimum. But can anyone like point out the potential disadvantage of this gradient descent algorithm? What's the potential issue?
You have to look through every example, every iteration to the solution.
So what's the
So for larger data sets.
yeah, exactly. Right. So when we look back to the computation of the gradient, right? We need to compute the particularity for each particular feature weight. We say the computation is a summation. The summation over all the training examples. So that means to perform one iteration, you need to go through the whole training set. Let us imagine you have like 1 billion or 10 billion training set. To compute a partial derivative for a one single weight, you have to go through the 10 billion training examples one by one. And if you happen to have like many features, like you have like 10,000 features, and how many computations do you have? 10 billion times 10,000, right? It's very low efficient because you just want to update, you just want to conduct one update of the weight vector, right? You need to go through the entire training set multiple times. You need to go through the multiple times. If you have like D features, you have to go through the entire data set for D times to just perform one update. So when your training set, when your training examples are huge, a huge number of training examples, it's very inefficient and very expensive to perform even for one update gradient descent. And unfortunately, this is a big data area. Right? This is time for big data. It's pretty common that you have like billions of training examples, millions of features. Very common. If your desktop does not have enough memory, laptop does not have enough memory, you cannot even load all the data into the memory to finish one computation. That means you won't be able to run this gradient descent algorithm. How can we deal with that case? That's why we are in practice, especially when we have a huge data, we often come to the so-called stochastic gradient descent. So what is stochastic gradient descent? It is motivated from the same observation here. Right? So we see that the weight vector, the whole weight vector, won't be updated until all training errors are computed. Right? The training error of each example are computed. Until all the training errors are computed, we'll finish one update. So the natural question would be, why not when we meet one example, compute the error just update? So now let's look at the design for the stochastic gradient descent. So we just repeat for each example, say xi, yi. And we pretend that the entire training set is just represented by this single example. The benefit is that I can use this single example to compute the gradient, then update the model accordingly. The biggest difference between the stochastic gradient descent and gradient descent is that the gradient descent makes one update to the weight vector for every pass over the entire data set. But for stochastic gradient descent, as long as I pass one training example, update the weight vector accordingly, and immediately. So you can imagine the updating procedure is much more efficient, much faster. So now let us look at the pseudocode for stochastic gradient descent. So similarly, we initialize our weight vector, say by W0, and then we go through many iterations until error is below some threshold. And then in stochastic gradient descent, this iteration is also called epochs. And then in each iteration of epoch, we look at each training example, say xi, yi. And then we calculate the error in predicting this particular example and multiply it with the corresponding feature, then update the weight vector, the feature weight accordingly. Question why here is a positive sign. Any idea?
Before we had the gradient, we had the negative grade from it, and every time you want to go down, descend the gradient. Right? So if you're going to descend it, you go through.
Yes. Yes, exactly. Right? I just want to track your attention. So we'll compute the gradient for some specific bit. Right? We have a minus sign outside, right? And we're doing gradient descent, meaning that we have to subtract the gradient by some multiply with some rate. Right? So we subtract some minus stuff. You end up being adding some stuff. That's why we have this update formula. But remember, this term is essentially treating xi, yi as a whole data set, then compute gradient. Then you update the corresponding weight. And in this way, after you process one training example, you update the whole weight vector, right? And then you go through the next example, you update the weight vector accordingly. So every time when you process one example, you just update the weight vector. And you do it again and again until the next iteration is again and again until convergence. This is called stochastic gradient descent. So first, what's the benefit of the? Let me first process. So this update rule is also called a Weizhou-Hopf rule in the neural network literature. But it is essentially stochastic gradient descent. So what's the benefit of the stochastic gradient descent in terms of the computation? And what kind of disadvantage do you have in mind?
So as you go through, you're updating your predictions, so you can start to get results a lot better. You're not waiting for the trillion computations that we're talking before to update the way that you might only be 1,000 size percent. And then start to go up. Ordering of your feature vectors might matter. If you have ones that give information early on, I don't know how big the ability is. Start clustering features
Yeah, that's kind of subtle, but yeah. So do you have any other comments?
Like real-time data, you're getting it like one example at a time. It'd be quicker, right? So you don't have to wait for the whole data set.
Yeah, that's the advantage, right? So what is the advantage? It probably have.
Is it not guaranteed to converge to the exact timeline? They will come close, but it won't necessarily be.
It actually has that guarantee. But later we'll discuss it. We'll discuss about it. Any other comments? So first, let us discuss about the advantages. So if we use batch gradient descent, you need to go through the entire training set before you finish one update. Right? So that means, say you have 1 billion examples, you have to go through the total 1 billion examples to finish one update. But for stochastic gradient descent, how many updates do you have? Like after you go through the entire data set once? 1 billion times, right? Because every time you pass the example, you update your model parameters. You update the weight vector in our case, right? So when you go through the entire data set, you have to make like 1 billion updates. So it's very efficient in updating the model parameters. Another thing is that it is feasible in whatever kind of computational devices, right? You don't need to worry about like my computer or my laptop does not have enough memory, right? Because we do not need to load the whole data into the memory once, right? We just need to load those examples one by one. You can even, if you like, you can even conduct stochastic gradient descent with your cell phone. But if you want to use your cell phone to do the batch gradient descent, you might need to like delete all your photos or videos. So the major benefit of stochastic gradient descent, very efficient updates of the model parameters. And second, it is very cheap to compute. You don't need to buy supercomputers. You don't need to buy like 100 or 1,000 gigabytes memory. But what is there's no free lunch, right? What is disadvantage? I believe your point is close to what I'm saying. But let me rephrase it again. Right? So when we treat the treat one single example as the entire training set and compute the gradient, is this gradient the true gradient of the objective function? Is this the true gradient? The answer is no, definitely. Our objective function is here, right? If you compute the gradient, the true gradient, the accurate gradient should be summation over the training examples. But now you just want to use one term inside summation as an approximation to the gradient. This is definitely wrong. So although the computation of each approximation is very, very cheap, so that we can perform many updates like in the same amount of time. Right? But every time you are updating your weight vector in the wrong direction. So the result will be like you update like 1,000 times might not be as effective as you update one time with the exact gradient. So that's the potential disadvantage. So in general, stochastic gradient, what's the behavior of stochastic gradient descent vector? You can imagine like you want to drive a car to your home, right? So if you use gradient descent, you are driving along the right direction, and everything is correct, and finally you end up with your home, right? Your destination. But if you use the stochastic gradient descent, it's like you got drunk. You got drunk, and you just drive around. But there's some guarantee. As long as you choose learning rate properly, you'll have a 100% sure chance, and it's almost a surety to finally arrive at your home, not at your neighbor's house. There's some guarantee on that. But the typical behaviors for stochastic gradient descent is like this. So overall, stochastic gradient descent is more favored in a large-scale environment. Why? Because in a large-scale environment, we want to look at more efficient updates rather than like waiting for 2 hours to see one update. And some theory shows that for as long as you have enough number of training examples, even you just do some random stochastic updates, when you go through enough number of samples, you have a large chance to get very close to the local minimum or some global minimum if we use the convex objective function. That's why the large scale applications we usually choose classic grid descent. But that does not mean grid descent is always better than batch grid descent. And if in a small medium case, people would rather choose the batch grid descent because the stochastic grid descent will run many iterations and updates until you get the right answer. So then let us talk about the learning rate basically. So in general case, if you want to conduct if you want to ensure the convergence of the grid descent, the stochastic grid descent, R must be decreased to 0 as long as with more and more training examples. And there is some kind of a decaying strategy along with number of iterations. And there's some, and also we have very elegant proof to show that within this decaying strategy, the model parameters will finally converge to some local minimum almost surely. Almost surely does not mean will always be, but just means with very large chance. And in some literatures, the learning rate is called step size. And there are more sophisticated algorithms to choose the step size automatically and converge faster. And you are not required to learn those strategies, but you're free to know that. And in the later lectures, I might present you with some famous step size adjusting framework like Eta Delta or the DAM principle, which are widely used in neural network learning procedure. You do not need to know why they adjust the step size like that. Why? Oh, we just print out the